Look up at the night sky. What you see, the stars, the galaxies, the faint dust of the Milky Way, is a grand illusion. It is a beautiful, intricate, and comforting lie, because what you see is not the universe. It is a mere fraction. A rounding error in the cosmic equation. The visible universe is the foam on the surface of a deep and unseen ocean. For centuries, we charted this foam. We measured its currents, predicted its tides. We believed we were mapping the ocean itself. We were wrong. The laws of physics, as we wrote them, worked perfectly for our luminous world. Gravity, electromagnetism, the great pillars of our understanding seemed unshakable. But in the quiet hum of distant galaxies, a dissonance began to grow. A single, stubborn observation that threatened to unravel everything. The observation was simple. Galaxies are spinning too fast. The stars on their outer edges are moving with such velocity they should, by all rights, be flung into the void. Yet they are not. They hold together, bound by a gravitational force with no visible source, an invisible hand holding the cosmos in its grip. It was the first clue, the first sign that the true ocean lay beneath the surface we knew. Something vast and dark was pulling the strings. We began a new accounting, a cosmic census. We weighed the galaxies, the stars, the gas and dust. We tallied every particle we could see. When the ledger was complete, the number was staggering. All the matter that we can see, everything that has ever been observed, makes up less than 5% of the universe. 95% is missing. Or rather, it is not missing. It is simply hidden. This is the story of that 95%. The story of the greatest hunt in the history of science. A search not for a new star or a distant world, but for the very substance of reality itself. We call it dark matter and dark energy, names given not to things we understand, but to the scale of our own ignorance. Dark matter is the invisible mass, the unseen architecture upon which the visible universe is built. Dark energy is the invisible force, the mysterious pressure pushing the fabric of space-time apart, accelerating the expansion of everything. Together, they are the silent, invisible majority, the deep currents and unseen leviathans of the cosmic ocean. They do not emit light, they do not reflect light, they do not interact with our world in any familiar way. And yet, their presence is undeniable. Their influence is etched into the very structure of the cosmos. To find them, we must look not with our eyes, but with our theories. Not with light, but with the subtle warping of space-time itself. The hunt requires us to descend, to leave the bright, familiar surface and venture into the profound and unsettling darkness below. It is a journey that challenges our most basic assumptions about matter, energy, and the nature of existence. Because the mystery is not just what the universe is made of. The mystery is what it means to exist in a universe whose fundamental nature is, to us, entirely alien. Our first target in this descent is dark matter. It accounts for roughly 27% of the universe. It is the invisible scaffolding, the cosmic skeleton, that dictates where luminous matter can coalesce and form galaxies. Without it, we would not exist. But how do you prove the existence of something that is, by its very nature, invisible? You look for its shadow. Not a shadow cast by blocking light, but a shadow cast by bending it. The phenomenon is called gravitational lensing, and it is our primary tool for mapping the unseen. Albert Einstein's theory of general relativity tells us that mass warps the fabric of space-time. Light, traveling through this warped space, follows a curved path. A massive object, therefore, acts like a lens, bending and magnifying the light from objects behind it. We can see this effect around massive galaxy clusters, where the light from distant background galaxies is distorted into strange arcs and rings. The problem is, the visible matter in these clusters isn't nearly enough to create the lensing we observe. The warping is far too extreme, the distortion far too severe. It is as if we are looking through a powerful lens, but can only see the faint outline of its frame. The vast majority of the glass, the mass doing the bending, is perfectly transparent. This discrepancy is not a small error. It is a direct visual confirmation that there is an enormous halo of invisible mass surrounding these galaxies. a colossal leviathan in the cosmic ocean whose only trace is the way it redirects the light swimming past. It is the ghost made visible by the ripples it creates in space-time. This evidence is not isolated. We see it everywhere we look with sufficient precision. The universe is filled with these invisible halos of matter. They are the seeds of cosmic structure. Another profound piece of evidence comes from the very beginning of time. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, a faint residual heat signature permeating all of space. It is a baby picture of the universe, taken when it was just 380,000 years old. This picture is not uniform. It has tiny temperature fluctuations, minuscule variations that represent the seeds of all future structures. These are the ripples in the primordial pond from which all galaxies would eventually form. Computer simulations allow us to model the evolution of these ripples over 13.8 billion years. If we run these simulations using only the 5% of normal, visible matter, the result is a universe that looks nothing like our own. The gravitational pull is too weak. The structures are too diffuse. Galaxies, stars, and planets never have a chance to form. The simulated universe remains a thin, unremarkable soup. It is a failed cosmos, a blueprint that never gets built. But when we add a massive component of cold, non-interactive dark matter to the simulation, the missing 27%, everything clicks into place. This invisible matter, immune to the radiation pressure that kept normal matter spread out, began clumping together much earlier. It created deep gravitational wells, or harbors, into which normal matter could later fall. The simulation now perfectly evolves into the cosmic web of galaxies and voids we see today. The CMB isn't just a picture, it's a recipe. And a key ingredient, the one that makes the entire structure possible, is dark matter. So we know it's there. The evidence from galactic rotation, gravitational lensing, and the CMB is overwhelming. But what is it? What kind of particle could possess these strange properties? The leading candidates are hypothetical particles called WIMPs, weakly interacting massive particles. Massive because they must provide the required gravitational pull. Weakly interacting because they do not engage with the electromagnetic force, which is why they are dark, or the strong nuclear force. They are ghosts in the machine of reality. Trillions of them may be passing through your body, through the Earth itself, every single second, and we feel nothing. They are adrift in the deep ocean, and our world of normal matter is like a porous net, offering no resistance to their passage. The hunt for WIMPs has driven humanity to build some of the most sensitive and isolated experiments ever conceived. To catch a whisper of a WIMP, you must first silence the roar of the cosmos. This means going deep underground. In abandoned mines, beneath mountains, scientists have built detectors shielded by kilometers of solid rock. This filters out the constant rain of cosmic rays and other radiation that bombards the Earth's surface. Inside these subterranean labs, vats of ultra-pure liquid xenon or germanium crystals are cooled to near absolute zero. The theory is that, very rarely, a WIMP passing through the detector will strike a nucleus, causing a minuscule flash of light or vibration. These are the most elaborate nets ever cast into the deep. They are designed to detect a single, phantom touch from an invisible world. Years pass. The detectors listen in perfect silence, waiting for a signal that has, so far, never come. The silence from these experiments has led some to question the WIMP paradigm. Perhaps dark matter is something else entirely. Another candidate is the axion, a much lighter, more numerous hypothetical particle. If WIMPs are like individual sharks swimming in the dark ocean, axions are more like a change in the water's density itself, a pervasive, field-like presence. Detecting them requires an entirely different kind of net, one that looks for faint conversions of axions into photons in the presence of intense magnetic fields. The hunt for dark matter forces us to confront the limits of our particle physics. The Standard Model, our spectacularly successful theory of all known particles and forces, has no room for a particle with the properties of dark matter. It is a complete theory of the 5%. But it is blind to the rest. This is not a failure, but an opportunity. The existence of dark matter is the single greatest piece of evidence that the standard model is incomplete. It points toward a new, deeper physics that lies beyond our current understanding. The invisible substance holding the galaxies together may also be the key to unlocking a more profound description of reality itself. The ghost in the cosmos is also a signpost, pointing the way to a new shore of knowledge. Another possibility, however remote, must be considered. What if there is no dark matter particle? What if the problem is not with the matter, but with our understanding of gravity? This is the central idea behind a controversial set of theories known as MOND, or modified Newtonian dynamics. MOND proposes that on very large galactic scales, the force of gravity does not behave as Einstein or Newton predicted. It suggests that at very low accelerations, gravity is slightly stronger than our current laws describe. This extra pull would eliminate the need for dark matter to explain galactic rotation curves. It is an elegant idea, but it struggles to explain the full range of evidence. While it can account for the rotation of individual galaxies, MOND has great difficulty explaining the gravitational lensing observed in galaxy clusters, or the precise patterns seen in the cosmic microwave background. To make it work, these theories often become more complex than the dark matter hypothesis they seek to replace. They suggest that our understanding of the ocean's currents is flawed, but the evidence suggests the currents are fine. There is simply a giant unseen creature swimming within them. And so, the search continues. In deep mines, in colossal particle accelerators, and in the patient gaze of telescopes, we are hunting for the architecture of our universe. The challenge is immense, the target elusive. But the stakes are nothing less than a complete picture of the cosmos. Dark matter forms the silent gravitational foundation of our world. It is the cosmic bedrock. But it is only one part of the darkness. Another, even more mysterious component dominates the universe's energy budget. An entity that is not pulling things together, but is actively, inexorably, pushing everything apart. We now turn our attention to the dominant force in the cosmos, dark energy. If dark matter is the unseen mass in the cosmic ocean, dark energy is the current itself, a mysterious, repulsive force inherent to the fabric of space. It accounts for an enormous 68% of the universe. The discovery of dark energy was a profound shock. For most of the 20th century, the biggest question in cosmology was whether the universe's expansion, initiated by the Big Bang, would continue forever or eventually reverse, collapsing in a big crunch. The answer depended on the universe's total density. If it was dense enough, gravity would eventually win, pulling everything back together. If not, it would expand forever, but gravity would act as a constant brake, slowing the expansion over time. No one was prepared for the third option. In the late 1990s, two independent teams of astronomers were using distant Type Ia supernovae as standard candles to measure the expansion rate of the universe. These cosmic explosions always have the same intrinsic brightness, so their apparent faintness tells us how far away they are. By measuring their distance and their redshift, how much their light has been stretched by the expansion of space, the astronomers could plot the history of cosmic expansion. They expected to see the expansion slowing down. Instead, they found the exact opposite. The distant supernovae were dimmer and thus farther away than they should have been. The only way to explain this was if the expansion of the universe was not slowing down, but speeding up. It was as if you threw a ball into the air, and instead of falling back down, it shot upwards with ever-increasing speed. The discovery was so revolutionary, it was awarded the Nobel Prize in Physics. Something was fighting against gravity on the largest scales. A pervasive energy, a pressure baked into space-time itself, was pushing galaxies away from each other at an accelerating rate. This is dark energy. It is the force driving the ultimate fate of our universe. What could this energy be? The most straightforward explanation is that it is the cosmological constant, a term Albert Einstein added to his equations of general relativity to allow for a static universe. When Edwin Hubble discovered the universe was expanding, Einstein famously called the cosmological constant his biggest blunder. He may have been wrong to discard it. In modern physics, this constant represents the energy of the vacuum, the energy of empty space itself. Quantum field theory predicts that empty space should not be empty at all. It should be fizzing with virtual particles constantly popping in and out of existence. This activity should give space its own intrinsic energy. The problem is, when we try to calculate how much energy the vacuum should have, the answer is horrifically wrong. Our best theories predict a vacuum energy that is 120 orders of magnitude greater than what we observe. That is a 1 followed by 120 zeros. It is the worst theoretical prediction in the history of physics. If the vacuum energy were this high, the universe would have torn itself apart in the first fraction of a second of its existence. The fact that we are here means our understanding of this fundamental energy is deeply, catastrophically flawed. This discrepancy is known as the cosmological constant problem. It is a gaping chasm between our theories of the very small, quantum mechanics, and the very large general relativity. Dark energy is not just a substance we need to find. It is a crisis at the heart of modern physics. Perhaps dark energy is not a constant at all. Other theories propose a dynamic field, dubbed quintessence, that changes over time and space. This would mean the repulsive force is not a fixed property of the vacuum. This is an even more speculative idea, but it is being tested. Telescopes like the Euclid Space Telescope and the Vera C. Rubin Observatory are designed to map the universe with unprecedented precision, tracking the history of cosmic expansion to see if dark energy has changed over eons. The implications of dark energy are profound and inescapable. It determines the final chapter of our universe. Because this repulsive force is a property of space itself, as space expands, more of this energy comes into being. As the universe gets bigger, the density of matter and dark matter decreases, but the density of dark energy remains constant. This means that, inevitably, dark energy will win. It is already the dominant component of the cosmos, and its dominance will only grow. This leads to a lonely and desolate future. As the expansion accelerates, galaxies not gravitationally bound to our own local group will be pushed away from us faster and faster. Eventually, they will cross a cosmic horizon, their light no longer able to reach us. The night sky in the far distant future will become nearly empty. Future astronomers will see only our own Milky Way galaxy, adrift in an endless, static void. They will have no evidence that other galaxies ever existed. The evidence of the Big Bang, of the cosmic expansion, will be erased. The universe will have hidden its own history. We may be living in the only epoch where a true understanding of cosmology is even possible. An even more extreme possibility is the Big Rip. If dark energy is not a constant and grows stronger over time, it could lead to a catastrophic end. In this scenario, the repulsive force would eventually become strong enough to overcome gravity on all scales. First, it would pull galaxy clusters apart. Then, galaxies themselves would be unbound. In the final moments, the force would overwhelm the electromagnetic forces holding solar systems and planets together. Finally, it would become strong enough to rip atoms apart. The very fabric of reality would be torn asunder. Dark energy is the quiet engine of the cosmos, pushing us toward a future of either infinite cold and isolation or violent dissolution. It is the ultimate expression of the unseen ocean's power. It is the deep current, pulling everything apart with a gentle, inexorable, and accelerating pressure. A force that arises from the vacuum itself, from the very nature of nothingness. The hunt for its nature is a race against time, a quest to understand the force that will define the end of all things before it erases the evidence of our own beginning. We have now charted the two great unknowns: dark matter, the scaffolding, and dark energy, the repulsive force. Together, they form the 95% of reality that lies beyond our senses. They are fundamentally different. Dark matter clumps together, pulling things in via gravity. Dark energy is smooth, uniform, and pushes things apart. Yet, they share one crucial property. They are dark. They do not interact with light. This shared property may be a coincidence, or it may be a clue to a deeper, unifying physics we have yet to imagine. Could there be a dark sector of the universe with its own particles and its own forces that only interacts with our world through the subtle touch of gravity? The hunt for these two entities is not just about filling in the cosmic pie chart. It's about understanding if we live on a small, luminous island, or if we are merely a transient pattern in a universe that is fundamentally and overwhelmingly dark. The intellectual journey into the dark universe is matched by a physical one. To find the faintest signals from the cosmos, we have built modern cathedrals of science. These are not just telescopes that see light, but instruments designed to perceive the universe through entirely new senses: gravity, subatomic particles, and the subtle warping of space-time. The Large Hadron Collider at CERN is a 27-kilometer ring designed to smash protons together at nearly the speed of light. It is a machine for recreating the conditions of the early universe. One of its primary goals is to create dark matter particles. If WIMPs exist, they could be produced in these violent collisions. They would not be seen directly in the detectors. Instead, their creation would be inferred from missing energy. The detectors would see the debris of the collision flying out in one direction, with nothing to balance the momentum on the other side. This imbalance would be the signature of a dark matter particle escaping unseen. While the LHC has been phenomenally successful, confirming the existence of the Higgs boson, it has so far found no evidence for WIMPs or any other new particles predicted by theories like supersymmetry. The silence from the LHC deepens the mystery. This pushes the hunt into even more sensitive domains. The underground direct detection experiments, like XENONNT and Lux Zeppelin, represent the pinnacle of this search. Imagine trying to hear a single pin drop in the middle of a hurricane. That is the challenge these experiments face. They are searching for a single WIMP interaction amidst a constant background of natural radioactivity. Every component must be meticulously scrubbed of any radioactive contaminants. The vats of liquid xenon are the purest materials on Earth. The sensors surrounding them are the most light-sensitive devices ever created. It is a painstaking, patient search, the scientific equivalent of a vigil. The researchers are waiting for a flicker of light from a world that is not supposed to emit light, a signal from the vast, silent majority of the universe. The search for dark energy requires a different approach. We cannot create it in a lab. We must observe its effects on the grandest possible scales. The Vera C. Rubin Observatory in Chile is a marvel of engineering. Its massive camera, the size of a small car, will survey the entire visible southern sky every few nights. Over a decade, it will produce a time-lapse movie of the universe, cataloging billions of galaxies. By precisely measuring their shapes and distances, it will create the largest, most detailed 3D map of the cosmos ever attempted. This map will allow cosmologists to track the influence of dark energy over cosmic time with unprecedented accuracy. They will look for subtle variations in the expansion rate, testing whether dark energy is truly a constant or something more dynamic. The Euclid Space Telescope has a similar mission. From its vantage point in space, free from the blurring effects of Earth's atmosphere, it will measure the distortion of galaxy shapes caused by gravitational lensing. By charting how the invisible scaffolding of dark matter has grown and evolved, and how the accelerating expansion has influenced that growth, Euclid will provide crucial new data points in our understanding of the dark universe. These are our deep-sea expeditions. The LHC smashes atoms, hoping a creature from the abyss will momentarily reveal itself in the flash. The underground detectors lay their silent nets, waiting for a gentle touch. And the great sky surveys map the currents, hoping to understand the force that drives them. The fact that these monumental efforts have so far yielded only silence is not a failure. It is a discovery in itself. It tells us that the dark universe is more subtle, more elusive, and perhaps more alien than our simplest models predicted. The lack of a WIMP signal has forced theorists back to the drawing board, invigorating the search for new ideas, like axions, sterile neutrinos, or even primordial black holes. It forces us to ask more profound questions. Is our entire approach flawed? Are we like ancient mariners trying to understand the ocean by tasting the salt in the water, when the true nature of the sea is in its immense pressure and hidden topography? The pursuit of the 95% is a testament to the human intellect's refusal to accept the surface as the whole story. It is an organized, global effort to perceive the imperceptible. It is driven by the most fundamental of all scientific impulses, the need to have a complete and honest accounting of our world, to know what reality is actually made of. Every null result, every silent detector refines the search. It closes one door, forcing us to look for another. It narrows the vast ocean of possibilities, guiding us toward an answer, even if that answer is something stranger than we can currently conceive. The hunt is not just about finding new particles. It is about testing the very limits of our knowledge and our technology. It is a process of peeling back the layers of reality, revealing a cosmos that is far darker, grander, and more mysterious than the one that meets the eye. In the face of this profound darkness, it is natural to question our foundations. The ongoing silence from our most sophisticated experiments has breathed new life into alternative ideas. We have already touched on MOND, the theory of modified gravity. While it struggles with large-scale structures, it remains a persistent and important intellectual foil to the dark matter paradigm. It reminds us that we must question our assumptions about gravity itself. Could gravity be an emergent phenomenon? Some theories, drawing on ideas from thermodynamics and information theory, propose that gravity is not a fundamental force at all, but a statistical effect, an entropic force. In this view, the extra gravity we attribute to dark matter might be a misunderstanding of how space-time information behaves on cosmic scales. This is highly speculative, but it shows the breadth of imagination being applied to the problem. The same is true for dark energy. Could the accelerating expansion be a sign that our universe is a brain floating in a higher dimensional space, and that gravity is leaking out into this larger bulk? These are ideas at the very edge of theoretical physics. They are difficult to test, and may not ultimately prove correct. But their existence is vital. They ensure that the hunt for the 95% is not a narrow search down a single path, but a broad exploration of every conceivable possibility. The problem of the dark universe is so profound that it may require not just a new particle, but a new principle of nature, a conceptual revolution on the scale of relativity or quantum mechanics. The core of the issue is this: all of our evidence for the dark universe is gravitational. We see its pull, we see its push, we have never detected it through any other force of nature. This could mean that gravity is our only window into this vast sector of reality. Or it could mean that we are misinterpreting gravity's own behavior. The universe forces us to hold both possibilities in mind. This intellectual tension is the engine of discovery. It fuels the debate between particle hunters and gravity modifiers. It ensures that every piece of data from our new telescopes and detectors will be scrutinized from multiple, competing perspectives. It is possible the answer will come from an unexpected direction: a strange signal from a gravitational wave detector, an anomaly in the orbits of stars at the center of our galaxy, a discovery in condensed matter physics that reveals a new type of emergent particle. The universe is a single, interconnected system. A clue to its largest mystery may be hiding in its smallest components. The hunt for the 95% has redefined the frontiers of cosmology and particle physics. It has brought these two fields together in a shared quest for a theory of everything that includes not just the light, but the darkness. It is a story of human ingenuity confronting cosmic ignorance, a story of building ever more sensitive instruments to probe a reality that seems designed to be hidden from us. And as we move into the final act of our journey, we must confront the most profound implication of all, not what the dark universe is, but what it means for us, the inhabitants of the 5%. Let us step back from the details of the hunt and consider the revelation that has been uncovered. The search for the 95% has given us more than just a new inventory of the cosmos. It has given us a new map of our own place within it. For all of human history, we have labored under the assumption that the universe was, in principle, knowable through light, that what we saw was a fair representation of the whole. This assumption is now shattered. We have discovered that we are the exception, not the rule. The matter that constitutes our bodies, our planet, and our stars, baryonic matter, is a cosmic afterthought. It is a mere contaminant in a universe that is fundamentally non-baryonic. We are not made of the same stuff as the universe we inhabit. Our existence is predicated on a form of matter that makes up a tiny fraction of the total mass, and we are suspended in a space whose very fabric is dominated by an energy that seeks to drive us into isolation. We are strangers in our own cosmos. Consider again the core analogy. The universe as a deep, dark ocean. We are not the ocean's primary inhabitants. We are the bioluminescent plankton, clinging to the surface, creating a thin, beautiful, but ultimately insignificant film of light. Our physics, our chemistry, our biology, it is the physics of the plankton, but the vast overwhelming reality is the cold, dark water below. The unseen currents of dark energy and the colossal, invisible leviathans of dark matter are the true masters of this realm. This realization reframes the Copernican principle. Copernicus taught us that we are not at the center of the universe. The discovery of the dark universe teaches us something far more profound. We are not even made of the same substance as the center. The universe is not just alien in its scale, but in its very essence. The periodic table, the foundation of our chemistry, is a catalog of cosmic impurities. The real story of the universe is written in a language of particles and forces to which we are, and may forever be, almost completely numb. What does this mean for the search for life? We scan the skies for planets like our own, assuming that life would arise from the same familiar chemistry. But if normal matter is the anomaly, perhaps life itself is the true cosmic rarity. Or, in a more speculative and unsettling thought, perhaps the universe is teeming with life, but life based not on the frail chemistry of baryonic matter, but on the unknown physics of the dark sector. A shadow biosphere on a galactic scale, utterly imperceptible to us. The darkness is not empty. It is the stage upon which the real cosmic drama unfolds. Dark matter particles, whatever they are, likely passed through the Earth's core as it formed. They are gravitationally bound to our galaxy, our solar system, and even to our own planet. We are constantly moving through a dense sea of this invisible substance. It is a second universe, coexisting in the same space as our own, interacting with our world only through the silent, persistent whisper of gravity. We are haunted, not by ghosts of the past, but by the very substance of the present. The discovery of the 95% is the ultimate antidote to arrogance. It is a humbling, clarifying revelation. It tells us that we are at the very beginning of our journey of understanding. We have spent centuries perfecting a science of the 5%, and we are only now, in this generation, developing the tools and the concepts to begin probing the true dark nature of reality. The age of cosmic discovery did not end with Hubble or Einstein. It has only just begun. The hunt for dark matter and dark energy is therefore more than a scientific problem. It is a philosophical imperative. It is the defining quest of our time, a challenge to expand our perception, to build new senses, to comprehend a reality that was not built for us. It is the next logical step in our evolution as a thinking species. We may never be able to hold a particle of dark matter in our hands. We may never be able to harness the power of dark energy. Their nature may be so alien that it forever eludes our direct grasp. But the act of searching, the intellectual journey itself, changes us. It forces us to build a more complete, more honest model of the universe. A model that acknowledges the vastness of our ignorance. A model that embraces the darkness not as a void, but as the repository of unknown knowledge. The universe is not missing. We were simply not looking in the right way. We were dazzled by the light, deaf to the gravitational symphony playing out all around us. The 95% is a reminder that the most profound truths are often hidden in plain sight, veiled only by our assumptions. It is a challenge to every future scientist and to every curious mind. The cosmos is not empty space dotted with light. It is a dense, interacting, and overwhelmingly dark entity, whose brightest sparks are but a footnote to its true story. To be human is to be a creature of the 5%, a denizen of the light, gazing out into an ocean of profound and beautiful darkness, and choosing to set sail. The hunt continues, the mystery endures, and in its shadow we find our purpose, to map the darkness, and in doing so, to truly understand the light. The universe is not what it seems. What we see is a luminous error, an exception to a dark rule. 95% of reality is a mystery, a gravitational ghost, an expanding void. We are made of the rare material, adrift in an alien ocean. The search for the darkness defines us, and the hunt has just begun